Hello, welcome to another problem session. This is another problem on finding entropy of ideal gas. We have one already, and this is the second one, which is very similar, except that now the temperatures are different here. The other problem we've done was exactly same, except the temperature was all same. Here the temperature is different. Trick is the same, that we find S1, S2, and then S final. So for B delta S is similar to SF minus S1 plus S2. So we need a formula for S. So if I given a T and V and N, so then of an ideal gas, what is S equal to, right? Okay. So we have done a little bit of that in the previous section or previous video, and we're going to do it again in a little more complete way. All right. So let's work one at a time. We are going to do temperature first. So when you mix like this, the energy does not change, right? The energy here is equal to energy here, because there's no energy. Total energy here is equal to total energy there. So energy, so let's call this energy U1, U2, and U. So we also have U equals to U1 plus U2. Now what is U? U depends on, if you remember, for ideal gas, you can have a du equals to nk let me write it down, n cv dt, or you can write on ideal gas the number, this is number of moles and this is molar, and you can use smaller cv dt if either way. So I'll just use that form, and if you integrate, u is going to be ncv t, and this is assuming constant cv, which is the case. Cv for ideal gas is number of degrees of freedom over 2 times R. Okay, this is the molar. So if I look at it, U for this will be, I got whatever, so this is like little n, this is n, so this whole thing will be 2n. So this is 2n degrees of 2 times R times T. So this will be the total energy at the end, and we have n times dF over 2 times RT1 plus n times dF over 2 RT2. So you can see all of this cancels out, and T is simply equals to T1 plus T2 over 2. Now if these guys have different number of moles, this will still work, and this will be weighed by the number of moles, fraction of how many came from here and how many came from here when they became together. So this is A. So T we found. How to get the B? We know first law is du is TdS minus P dV, right? So we want S. So ds is du over T plus P over T dV. Of course, P over T can be replaced by N R over V, and so this thing is and du is replaced by N CV dt. So if I have a temperature some small epsilon and pressure some A to temperature T and pressure P, volume V, let's look at volume equals to say B. From here to there, delta S should be just integrate this guy, right? So this will be entropy S, and this will be entropy reference. So S minus S reference, and we can always scale reference to 0, okay? Because we're always concerned with subtraction, and the reference will all cancel out in the subtraction. So S minus reference will be N CV log T. So the minus it's plus, actually, plus N R log V. Okay, so that's minus this NCV log epsilon plus NR log B. So this is just a constant reference, and I'm just going to ignore from now on. So we just say the S of a state is just going to be NCV log T plus NR log V. So this, I'm going to just assume that reference is this, and we're just going to cancel out the reference from both sides. And so this is going to be a formula we'll use on each one of them. All right. So we have delta S was the final. So what's the final temperature? And number of moles is 2N, and CV is the same. And you have a log this T1 plus T2 over 2. And then this guy is NR, 2NR log V1 plus V2. That's the final. From there, I'm going to subtract each one of them, right? So I'm going to subtract NCV log T1 plus NR log V1. For one of them, I'm going to subtract the other one, NCV log T2 plus NR log V2. So that's the answer. I can, simplify it a little bit, but that should tell you how one can proceed when handling problems in entropy of an ideal gas, even when the temperature is actually changing, right? So because the energy is a function of temperature only through this, we are really in a very good position when we deal with ideal gas. So that's, I think this is a cute little problem, and sometimes shows up in tests. Okay, so I'll see you in another video. Bye.